So in this, in chapter 2, we talk about the properties of an atom. We describe an atom as having a nucleus, which is made up of protons and neutrons. And then we talk about electrons. And so in this lecture, what we're going to describe is where an electron is in an atom. And so to do that, we need to look at its electronic structure as well. And so unlike the solar system, which has planets that revolve around the sun in a particular orbit, the electron is actually confined to a region. So it's not actually a direct path. It's more like a region or a cloud around the nucleus, and it has a particular energy with it. And if you were to continue in general chemistry, you would actually use the equations to calculate the energy of where the electron is. And we say that these electrons occupy energy levels, which we refer to as shells or principal energy levels. So the first shell is 1. So there's no 0 energy level, because 0 would signify that it's in the nucleus, and electrons can't go to the nucleus. So the first energy level starts with a 1 and it goes to infinity. So we start with n equal 1, 2, 3, and it continues. And so the higher the energy level, the further away an electron is from the nucleus. So you can imagine that those elements that have high number of electrons, they have many different energy levels. And so some of those electrons are very far from the nucleus of the atom. And so we're going to start, when we're looking at electrons, start in the lower number shells and then work our way to higher number. Just imagine you're starting on a staircase. You start at ground level, you start walking up the stairs. We're going to be doing the same thing with electrons. We start at the lower number shells or energy levels, and we start working our way up as we fill those to higher energy levels. And so again, principal energy level tells you how far the electron is from the nucleus. And on the periodic table, we'll see that N actually goes up to 7. So the periodic table, the maximum energy level is 7. So once you get to the 7th energy level, that's the highest you can go on the periodic table. And if you look at the periodic table, you'll notice that there are 7 rows on the periodic table, each row corresponding to a energy level. So, and the way we can determine the number of electrons in an energy level is by using this equation here, which is 2n squared. So n is the energy level. You square it and then multiply it by 2, you get the maximum number of electrons in that particular energy level. So as I said, on the periodic table, it goes up to 7 energy levels. It can hold more electrons than the 3rd energy level, for example. So this is kind of a chart to show you, as you get to higher energy levels, you increase the number of electrons you can have. So for the first energy level, it can only hold 2 electrons. And if you take notice and look at the first row on the periodic table, you see it only has 2 elements in it. It has hydrogen and helium. If you go to the 2nd energy level, you have 8 electrons. And if you look at the periodic table, you look at the 2nd row, it goes from lithium to neon. And if you count the number of elements, you get 8. So the periodic table is very closely related to how electrons feel in energy levels. So again, energy level 1 has 2 electrons, just like the row 1 or period 1 as it's called, has two elements. And if you go to row 2, it has 8 elements. Now row 3 and 4 are a little bit different, but they do coincide with 18 and 32. But those are a little bit different on how they get to 18 elements and 32 elements. But regardless, if you want to know the number of electrons in an energy level, you can use this equation here, 2n squared. And n is the principal energy level. And by the way, n is always positive. It's never a negative number. And so within each energy level, we have what are called subshells. So the energy levels are called shells. Within those shells, you have subshells. So just imagine you have an onion. When you peel one layer, you have more layers within it. So with the shells, you have, say, energy level 1 is a shell. Within that shell, you have subshells, which are represented by these letters S, P, D, and F. And these are actually different types of what we refer to as orbitals or regions where the electron can be. It's not an actual location, it's a region. So within this region, an electron can be located here. Just like if we were to say in San Antonio, if I was to stick my hand into a box and call it San Antonio, there's a chance that in that region I can pull out Dr. Armand because he's in that region of San Antonio. Just like these electrons are in these different subshells, if you were to reach your hand in there, you have a high probability of grabbing an electron. And there are 4 types of subshells we use. And there are more types of subshells, but these are the 4 major ones, S, P, D, and F. And these are also the ones that are used with the periodic table as well. But in addition to S, P, D, and F, there's also, it keeps on going down the alphabet, G, H, etc. But for the periodic table, we only go to the F subshell. So within different shells, aka energy levels, we have subshells, which are called aka orbitals. And so these subshells have orbitals in it, and these orbitals have different shapes. One looks like a ball, one looks like a bow tie, etc. And this is what I mentioned earlier. So this orbital is not an actual orbit like a planet orbits around the sun. It's a region of space where you have a high probability of finding an electron. So it's just in this region, the electron is somewhere there. We don't know the exact location of an electron. We just know it's in this region here. And this is actually very important. Each orbital can hold 2 electrons. So we have a shell, which is the energy level. Within this shell, we have a subshell. And within the subshell, we have orbitals. So orbitals make up subshells, and the subshells make up the shell. So again, the shell is the energy level. The subshell is defined by these letters S, P, D, and F, which are kind of like the types of orbitals. And then with each subshell, you have orbitals in it. And each orbital can only hold maximum 2 electrons. And so this tells you the number of orbitals for each subshell. So the S orbital can only have 1 orbital, so it has a maximum of 2 electrons. So the S subshell can only have a maximum of 2 electrons, whereas the P subshell can have a maximum of 6 electrons, because each orbital, again, can hold 2 electrons. And then the D orbital can hold a maximum of 10 electrons. And then finally F, a maximum of 14 electrons. So if I was to draw these orbitals as dashes, clear out some room here. And again, we're describing where an electron is in an atom. So for the S subshell, we usually denote it with a dash. So one dash means one orbital, and you can hold 2 electrons, which we draw as arrows. And then the P subshell has 3 orbitals. And again, each one of these dashes can hold 2 electrons, and that's where it gets the 6 electrons from. And then D would have 5 dashes with 2 electrons in each, and then F would have 7 dashes, which would be a total of 14 electrons. So as you go down to higher energy levels, or you go up to higher energy levels, you're going to have more subshells in it, which means you're going to have more number of electrons in that energy level. And you increase in energy as you go down the subshell for a particular shell. So this is kind of an overview to show you in each energy level what types of shells and orbitals are present. So again, the 1s orbital is in the first energy level. Now the energy level tells you the number of different types of orbitals. So first energy level just has an s orbital. The second energy level has an s and a p orbital. Third energy level has 3 types of orbitals, the s, p, and d. And then lastly, the last type of orbital we deal with is s, and the fourth energy level is where we start seeing the appearance of the f subshell. So again, the energy level or shell tells you the number of different types of orbitals that energy level, aka shell, can have. And as you see over here, this is where we get the maximum number of electrons. So the s orbital holds 2, the p orbital holds 6. That's where we get 8 electrons for the second energy level. For the third shell or energy level, s can hold 2, p can hold 6, and d can hold 10. That's where we get the total 18 electrons. So depending on how many electrons you have, you start with the lower energy level and you start working your way up. And there are some rules to know which shells and orbitals are lower in energy than others. Continue. So this is just showing you, for example, the different shapes of the orbitals. So most commonly we show you what the s orbital looks like and the p orbitals. So for the s orbital, it's just a spherical shaped orbital with the nucleus in the center. So if you think of a ball, that's what the s orbital looks like. And so if you were to stick your hand in this ball, you have a high probability of grabbing an electron. Now for the p shell, we said, or p subshell, we said there were 3 orbitals, and that's referred to as the pz, px, and py. And so it just depends on what I like to refer to as a bow tie, which axis the bow tie is along. And so since you can orient this bow tie in 3 directions, that's why the p orbital has 3, or the p subshell has 3 orbitals, because they're all oriented 90 degrees apart from one another. So when you put them all together, it looks like this on the far right. So you can imagine with the d orbital, which has 5, or the d subshell, which has 5 orbitals, it's going to have 5 different shapes for each of the different orbitals. Now when we go to what's called the electron configuration, we're showing how the electrons are arranged in the atom's orbital. So we identify how many electrons are in each of the different energy levels and subshells, aka orbitals, for each element. And so knowing the number of electrons for the elements, which we get from the atomic number, we can start filling electrons in the different types of orbitals. So one thing we need to remember is we always start at the ground state, which is the lowest energy arrangement. So you start putting electrons in at the lower energy levels before you start filling them in higher energy levels. So there's some rules that we need to follow when writing the electronic configuration. And so we always start with the 1s orbital. So anytime you fill electron configuration, we start from the 1s. Once that's filled, we go to the second energy level. We fill both of those types of orbitals, and then we move to the third, fourth, etc. So you always fill it in increasing energy orbitals, and you always start with the 1s orbital. You don't start with the 2s, you start with the 1s and work your way up. And so this is the diagram that we follow when filling the orbitals. And so see, most of it we start from the 1s, we go to the 2s, to the 2p, the 3s, the 3p, and you'll notice at the 3p there's a little bit of deviation because after the 3p comes the 4s and then the 3d. And then we have 4p, and then the 5s comes before the 4d. And so once you get to the fourth row on the periodic table, the 4s, the s orbital for that row comes before the d orbital of that row. So the 3d orbital comes after the 4s orbital. And when we look at the periodic table, I'll show you how you can identify this filling within the periodic table. Then we look at 6s. After 6s, we introduce the 4f orbital, then the 5d. And again, once we look at a periodic table, I'll show you all the tricks in knowing how to fill electron configuration. But you always start with the 1s and you work your way up. So as you have more electrons, you put them in more orbitals and you work your way up to the higher orbitals. Now, all the orbitals shown here are all the ones that you're going to use for the periodic table. So you won't go, actually there's one missing, 7p, but you won't go above 7p. So after 6d would be 7p. After that, we don't go any higher in regards to orbitals for the periodic table. The largest elements would end at 7p. So if you remember this is all the orbitals that you'll encounter on a periodic table. So again, the first rule is we start from the lowest energy level, work our way up. The next rule is that each orbital holds a maximum of 2 electrons. So each one of those boxes on the previous slide here, each box can hold 2 electrons in it. So you can't put more than 2 in each box. Now, when you have orbitals that are equal in energy, you have to put 1 electron in each until you start pairing them up. And so what does that mean? If we go back to the previous slide, the orbitals which have more than 1 box, such as the p orbital, the d orbital, and the f orbital, it means that you have to fill 1 electron in each before you go back and pair them up. So that's what that rule means. So 3 rules. We start with the lowest energy level, and fill our electrons from the lowest energy level up. That's rule number one. Rule number two is that each box gets 2 electrons. One is pointing up, one is pointing down. The third rule is these orbitals that have multiple, or the subshells that have multiple boxes, you put 1 electron in each before you pair them up. So you have to remember those 3 rules when doing electronic configuration. Now the way we illustrate or visualize these electrons is by using what's called an orbital diagram, which, as we saw on the 2 slides back, is that diagram with the boxes, and we use arrows to represent the electrons in the orbitals. So each box represents an orbital, and then when we have only one arrow in the box, it's referred to as an unpaired electron, and it's always pointing up when you put it in the box first. Then when you put the second electron in the box, you always have it pointing down, and now you have a pair of electrons. So unpaired or lone electron means that only one electron is in the box. Paired electrons means you have 2 electrons, one pointing up and one pointing down in the box. So if a question asks, draw the orbital diagram of an element, you would draw the orbitals as boxes, and instead of writing the total number of electrons, you would put the arrows to represent electrons. So the reason that we put one up and one down is because they have paired spins, which means they're opposite directions. So one is, we call it clockwise, one is counterclockwise. So now if we look at the first row elements, and these are the elements on row 1, we're talking about hydrogen and helium. So hydrogen, if you look at its atomic number, has 1 electron. So the way we would write its orbital notation is 1s, and then we put 1 box above it, signifying that the s orbital has 1 type of orbital. And then we fill it with the 1 electron. So notice that hydrogen has 1 lone electron in it. And then the electron configuration we write as 1s and the superscript 1. So the 1s1 tells us that we are on the first energy level. We're in the s subshell / s orbital, and there's 1 electron in it. Now if we go to helium, helium has 2 electrons. Again, we start with the 1s orbital. Now it can hold a maximum of 2 electrons, so we put both electrons in there, and its electron configuration is 1s2. So hydrogen is very reactive because it only has this 1 electron, but helium is very inactive because it's all paired up. So just by adding 1 electron, you change the chemical properties of an element. And so again, we start at the lowest energy level, which is 1s. Since we didn't fill that completely, we didn't have extra electrons to put in, we stopped at the 1s. We went 1s1 and then 1s2. Now if we go to the second row, we're talking about elements lithium through neon. Now lithium has 3 electrons, so we're going to need the 1s orbital, and once that's filled, we're going to need the 2s, because the 1s can only hold 2 electrons. So we're going to have 1 electron left over, so it needs to go into the 2s orbital. So we put 2 electrons in the 1s orbital, then we move to the next energy level and put 1 more electron into the 2s orbital. And it's because of this 1 lone electron that lithium, as we'll see in our next lecture on ionic naming compounds, that lithium likes to have a +1 charge. And the electron configuration would be 1s2, 2s1. Now if we go to carbon, which is further down row 2, it has 6 electrons. So we're going to need the 1s orbital, the 2s orbital, and the 2p orbital. Because each s orbital can hold 2, we're still going to have 2 electrons left over. So we're going to need to add them to the 2p orbital. And so again, we completely fill the 2s orbital and the 1s orbital. But for the 2p orbital, you have to give each orbital 1 before you pair it up. So here you notice that we give 1 electron into each 2p orbital. Because there are 2 left over, we don't pair them up, because this violates rule number 3 that we talked about. So each one gets 1 electron before you go back and start pairing them up. So carbon has 2 lone electrons. So it'd be 1s2, 2s2, 2p2. And then lastly, we look at neon. Neon has 10 electrons. So again, we get the number of electrons from the atomic number on the periodic table. So again, we're going to need the 1s orbital, the 2s orbital, and the 2p. So each s orbital can hold 2 electrons. So 4 minus 10 gives us 6. So the other 6 electrons need to go into the 2p orbitals. So here you'll notice all of the orbitals are completely filled, and it contains only paired electrons in it. And so the electron configuration would be 1s2, 2s2, 2p6. And this is why neon and other noble gases are very inert, is because they have a field, completely filled orbitals. So it doesn't want to react that much because it's happy with the electrons that it has.
Oh, me?
Yeah.
Oh, you said we're going to go ahead and continue.
So as you can imagine, as we get to larger and larger elements, it becomes more tedious to have to write everything from 1s to 2s to 2p to 3s to 3p, etc. So there's a way that we write the shortened or abbreviated electron configuration using the noble gas notation. So what we'll do is when we're writing the electron configuration, we look for the previous noble gas and we put that in brackets, and we only put the important part of that particular element after the noble gas. And the reason we choose the noble gases is because noble gases are very stable elements. So for example, we looked at lithium. Lithium is 3 electrons. The electron configuration is 1s2, 2s1. Oops. And now if you look at the periodic table, you'll notice that the preceding noble gas to lithium is helium. So we can rewrite this as, we put helium in brackets, and so the 1s2 is represented by helium, and then we have the important part for lithium, which is 2s1. And so this is the shortened or abbreviated notation for lithium. So again, when we write the helium in brackets, it's referring to the 1s2, because 1s2 is the electron configuration of helium. Now if we look at carbon, we looked at carbon on the previous slide. So carbon has 6 electrons. So we go 1s2, 2s2, 2p2. And if you look at carbon, the preceding noble gas is helium. So now if we want to write the shorthand, we start with helium. And then helium represents 1s2, so we only put what is unique after 1s2. And this is the abbreviated electron configuration for carbon. So you're always looking at the previous noble gas to see which one it is, and then after that you only write the unique part of it. So here we have carbon. The nearest noble gas is helium, which is represented by the 1s2. And so this is how we write the abbreviated electron configuration. Now, if we look at something a little bit heavier, let's say we look at sodium. Sodium has 11 electrons. So again, we start 1s2, 2s2, 2p6, and then after 2p becomes 3s1. And again, I'm following that chart from a few slides back. So now if we were to write the shorthand abbreviation or the shortened noble gas or electron configuration, you would start looking for the last completely filled p orbital. So the last completely filled p orbital is 2p. So everything from 1s to 2p is represented by neon. And so if you weren't sure that 2p represented neon, what you do is you start from helium and you count 2 down. You'll see that you end up on neon. So since neon represents 1s2 to 2p6, the abbreviated notation would be neon 3s1. And this is why, as we'll learn in a little bit, why sodium likes to be +1, because if it gets rid of this one electron, it becomes like neon, which is more stable. And so this is how we write the shortened or abbreviated electron configuration. So here if we look at calcium, now we're getting to bigger elements. Calcium has 20 electrons, so it's on row 4. Now again, we start with the 1s, we completely fill it, we go to the 2s, the 2p, 3s, and then notice after 3p, we don't go to 3d, we go to the 4s. And if you look at that chart, you'll see that the 4s comes before the 3d. And so the 4s is lower in energy than the 3d orbital. And this is for any row you're on. The s orbital is going to be lower in energy than the d orbital with one lower energy level. So 5s is lower than 4d, 6s is lower than 5d, 7s is lower than 6d. And so here when we write the electron configuration, you'll see that it's 1s2 to 4s2. But notice here that the last filled p orbital, completely filled p orbital, is a 3. And if you go to the periodic table and count 3 noble gases down from helium, you'll see that it'll end up on argon. So argon is represented by 1s2 to 3p6. So instead of writing all of that, we can just write argon 4s2. And again, we'll see in a little while, calcium likes to have a +2 charge because calcium likes to get rid of these 2 electrons to be like argon. And so this is good. This is the periodic table, and this kind of shows you the filling order. So if you notice this on the periodic table, you start with 1s, you go left to right, you go 2s, 2p, notice here 3s, 3p, and then at 4s, then we have 3d. Notice that the d orbital, the energy level of the d orbital is 1 less than the row it's on. So if you see a d orbital on row 4, it's going to be the 3d orbital. So it's always going to be n minus 1 is the d orbital, So n is the period or row number. So if you want to know what d orbital you're on, just take the row number, subtract 1, and that's the d orbital. Now for the s orbitals and the p orbitals, those correlate to the row that you're on. So if you're on row 5, you'll see that we have the 5s and 5p. If we're on row 4, we have the 4s and the 4p. Now the f orbitals, we only have two, 4f and 5f are 2 minus the row they're on. So 4f is actually on row 6 and 5s is actually on row 7. So 7 minus 2 gives us 5 and 6 minus 2 gives us 4. Now this actually is a mirror image of the periodic table. So for example, you see 2s. Well, this correlates to lithium and beryllium. So if you see that you have lithium or beryllium, you know that the last orbital you're going to fill is the 2s orbital. If you have, for example, iron, which is right here, the last orbital you're going to fill is a 3d orbital. So if you kind of look at the periodic table and see where does your element fall in relation to this, that'll tell you the last orbital filled for that particular element. So here, if we write the noble gases, we have helium, we have neon, we have argon, krypton, I want to say xenon, and radon, which is Rn, I believe. And so if we want to write the shorthand configuration of iron, well, we know that the preceding noble gas is argon. And then we just write what is left over. So we know that it's 4s2, 3d6. So you don't have to write the whole thing. You can just write only the abbreviated notation. If we look at, for example, let's see, nitrogen, phosphorus, antimony, which is right here, you see antimony falls in the 5p block. So that tells you the last orbital filled for antimony is the 5p. And if you count, you go here 1, 2, 3, it's going to tell you that in the 5p orbital is going to have 3 electrons. And so the preceding noble gas is krypton. So if we were to write the shorthand for this, it'd be krypton. Excuse me. For antimony, would be krypton 5s2, 4d10, 5p3. Because again, it's in the third group on the p, what we call p block. So it's going to have 3 p electrons. The middle group is called the d block. And so if you count here, if it's on this column, it's going to have 1 d electron. If it's on this one, it has 2, 3, 4, 5, 6. So what I'm writing is the number of d electrons for those elements that are in that column. The same goes for the p block. It's 1, 2, 3, 4, 5, 6. So again, it tells you, excluding helium, of course, it tells you the number of electrons for that particular p block element, or d block, and of course s block would be 1, 2. F has similar as well, but we don't really delve into the F block that much, so I won't include that here. So again, if your element is, say, here, the last orbital field is going to be 4d, and it's going to have 3 electrons. So it would be krypton 5s2, 4d3. If your element is here, for example, it's going to have 8d electrons. It's going to be krypton 5s2, 4d8. So again, the periodic table does a good job of mirroring the filling order of electrons for electron configuration. So here we want to write the shorthand electron configuration and the orbital diagram for these elements. And so in the bottom, I have that chart that we used on the previous slide. And so here we have cadmium. And if you have a periodic table handy, it'll be good to go and see where cadmium is. And when you look at the periodic table, you'll notice cadmium is right here. So this tells you that cadmium is a d block element, meaning that the last orbital field is a d orbital. So all transition metals are d block elements, meaning that they fill the last orbital field is a d orbital. So here we have cadmium, and if we look, the preceding noble gas is krypton. So everything up to 4p can be represented by krypton, and the only unique part of cadmium is the 5s2, and this would be the 4d10. So if we were to write the electron configuration, it would be krypton 5s2, 4d10. So it has a completely filled s orbital and d orbital. Now if we were to look at the orbital diagram, the abbreviated orbital diagram, we have krypton, we have the 5s orbital and the 4d orbital. So now we're going to add electrons. And so cadmium is very stable because it has no lone electrons. And so this would be the orbital diagram, or the abbreviated orbital diagram of cadmium. Next we go to arsenic, As, and if you look at the periodic table, arsenic's on the 4th row, and so it's right here. It's a p block element, meaning that the last orbital field is a p orbital, and the row that arsenic's on will tell you what the last p orbital is. It's on the 4th row, so it'll be 4p. And the preceding noble gas is argon. So everything up to 3p can be represented by argon, and then the unique portion for arsenic is the 4s, 3d, and 4p. So if we were to write this electron configuration, it'd be argon 4s2, 3d10, 4p3. Now the abbreviated orbital diagram would look like this. So we'd have argon, and then we need 1 dash for the s orbital, 5 for the d, and 3 for the p. So this abbreviated form is a lot easier to write than the extended. So now we start filling in electrons. So the 3D is completely filled. Now for the 4P, we have 3. So each one gets 1 in it before we pair it up. And so this is the abbreviated orbital diagram for arsenic. Next we have yttrium, which is Y. And if we look on the periodic table, yttrium is on the 5th row and it's located right here. So again, yttrium is a transition metal. It's on the 5th row, so it's going to be the 4d orbital, is the last orbital filled. The preceding noble gas is krypton, and so the electron configuration would be krypton, 5s2, 4d1. And if we were to write the orbital diagram, we would start with krypton, 5s2. Even though there's only one d electron, you still have to draw all 5 dashes or boxes to signify that it's a d subshell. That would be the orbital diagram for krypton. Last, we have palladium. So if we look at the periodic table, we find out where palladium is. It's a transition metal. It's located right here. So again, it's a transition metal. It's going to end in a d orbital, and since it's on row 5, the d orbital will be 1 minus the row, which is 4d. Preceding noble gas is krypton. So this would be krypton, 5s2, 4d8. Now if we do the orbital diagram, krypton, we have the 5s orbital and the 4d orbital. So the 5s gets 2 electrons, the 4d gets 8. But remember, you have to give each orbital 1 electron before you pair them up. So that's the orbital diagram for palladium. Now, for some transition metals, there are exceptions, but we're not going to cover those exceptions in this course. If you take a higher level general chemistry course to actually talk about the exceptions for transition metals, but for this course, we're not going to concern ourselves with the exceptions. So with periodic trends, there's 3 periodic trends we're going to talk about. The first one is what we call valence electrons. And these are the electrons that are involved in the bonding or the chemical reactions that we talk about. And so these occur in what's called the valence shell. And the valence shell is the last energy shell in the electron configuration that we wrote for the elements, the highest energy. So when you write the shorthand abbreviation electron configuration, the highest energy level left will be the valence shell. And we're looking for the highest. So it's going to be, for example, if I wrote lithium, lithium is helium 3s1. So the valence shell here would be the the 3s orbital, so it only has one valence electron. Whereas, for example, if I did phosphorus, phosphorus would be neon 3s2 3p 3. So here for phosphorus, the highest energy level is 3, and we have both a 3s and a 3p. So you have to include them both for valence electrons. So phosphorus would have 5 valence electrons. If we look at one more, let's say we look at selenium. And selenium would be argon 4s2 3d10 and 4p4. So again, you have to look at the highest energy level. So here for selenium, the highest energy level is 4. So we have a total of 6 valence electrons. So again, the valence electrons are the highest energy level orbitals, which may include an s orbital if it's a metal. If it's a non-metal, it will include an s and p orbital. And we're not going to delve into transition metals. Those are a little bit different. We're just going to deal with main group elements, which is your group 1, 2, and 13 through 18. So if it's a metal, if it's a main group metal like group 1 or group 2, the last filled s orbital is going to be the valence orbitals. If it's a non-metal, or it's in groups 13 through 18, it's going to be both the last filled s and p orbitals. So we call it valence or outermost shell. And again, it's the highest value of n. So for beryllium, we go 1s2, 2s2. The 2s is the highest energy orbital. So beryllium has 2 valence electrons. Again, it's an s block metal. All s block metals, the last filled s orbital tells you the number of valence electrons. Now, chlorine is a p block non-metal, and so for p block elements, the last filled s, the highest filled s and p orbitals tell you the valence electrons here. So the valence shell is 3. Number of valence electrons is 7. And so as you go from left to right on the periodic table, the number of valence electrons increases. And when we're just talking about main group elements, the total number of valence electrons you can have is 8. You can't go higher than 8 for main group elements. Again, main group elements are those elements such as group 1, group 2, and group 13 or 3A through 18, or you call it 8A. So there's a way we can relate the valence electrons to the group number. And this is very important. Elements in the same group have the same number of valence electrons regardless of what row it's on. And this is because they have similar electron configurations, which means they have both have, for example, an S and P orbital field. It's just on different energy levels. So group 1A through 18A, or group 1 through 8A, or group 1 to 13 through 18, the group number equals the number of valence electrons. So for example, group 1 is contains lithium, sodium, etc. They have one valence electron all the way to group 8A. So the A's, whenever you see the A after the number for the group, that's excluding the transition metals, because the transition metals are B's. So 1A through 8A is just your main group elements. Of course, helium is the exception, because helium only has 2 valence electrons, but it is a noble gas. So that's one exception there. And so all these elements in the same group have similar chemical properties because they all have similar number of valence electrons. So again, if I was to draw the periodic table, and we're just looking at main group, so we're going to disregard transition metals. As you go left to right, valence electrons increase. And so the maximum number of valence electrons you can have is 8, and the noble gases have 8 valence electrons. So this is just showing you kind of like the different periods. So period 1, 1A, hydrogen has 1 valence electron. We go to period 2. We see that as we go across period 2, depending on the group number, we see the number of valence electrons increase. So lithium has 1, carbon has 4, oxygen is in 6A, it has 6, neon has 8. And later on, when we talk about ions, the ions like to gain or lose electrons in order to have 8 valence electrons. For example, fluorine likes to gain 1 electron to become like neon. So fluorine likes to have a -1 charge, whereas lithium likes to lose its valence electron to have a +1 charge. Yeah, so again, we're only going to be relating to main group elements. The transition metals, there are some that have exceptions, but we're not going to delve into those exceptions about transition metals. You can write lithium as 2s1, or you can, when I put the caret, that just represents a superscript. So it's the same, whether you put it like this, or you write lithium like this. The only reason it's written with a caret here is because I don't have the ability to write it as a superscript. But the main thing is to note that it's known as you go from left to right, as the group number increases, the number of valence electrons increase. Same thing with row 3, it correlates to the group number as well. So with valence electrons, we like to write electron dot symbols to show the number of electrons in the valence shell. And each dot represents a valence electron. And so you can imagine we have 4 sides of an element symbol. So each side can have 2, so that's a total of 8 valence electrons that can fit around an element. So if you have more than 4 valence electrons, you have to pair them up. For example, Oxygen has 6 valence electrons. So you have more than 4, you're going to have to pair them in pairs. So for example, we write the Lewis dot structure of oxygen. It has 6 valence electrons, so we go 1, 2, 3, 4, 5, 6. If we look at fluorine, which has 7, it'd be 1, 2, 3, 4, 5, 6, 7. So that's the Lewis dot symbol for oxygen and fluorine. So again, you take the number of valence electrons for each element and you apply them as dots. And these dots look ugly. So let me clear that up. So I'll draw. So hydrogen would look like this. Carbon, like that. We've already done oxygen. And again, these are the electrons that are involved in bonding. So in later chapters, when we're drawing Lewis structures, we'll be using the Lewis dot symbols. Sure. All right. So this is one periodic trend, valence electrons. Another periodic trend is atomic size. So as you can imagine, as we move from left to right, top to bottom, the size of atoms differ. And you can correlate the atomic size to the number of valence electrons. So the fewer valence electrons, as we go from left to right, we increase in valence electrons. So the elements on the same row with the fewer valence electrons are going to have a larger atomic size than the elements on the same row with more valence electrons. Because what happens is when you have more valence electrons, as you go from left to right, they're going to be more attracted to the nucleus, and so your atomic size shrinks as you go from left to right. But as you go down a group, atomic size increases, because as you go down a group, you increase the number of electrons, aka more energy levels. So as you add more energy levels, the atoms get bigger. Whereas when you go from left to right, you're adding electrons to the same energy level. So as you add electrons to the same energy level, they have greater attraction to the nucleus, which causes the radius to shrink. So as you go down a group, it increases atomic size. And as you go from right to left, it increases. So for example, fluorine and neon are very small, but francium and rubidium are very large, kind of like the opposite ends of the size. So again, the number of valence electrons increases from left to right. So as you increase the number of valence electrons, you also increase the number of protons. It pulls those electrons closer to the nucleus, because those valence electrons have less bodyguards, which are called the inner electrons, to protect them from the attraction of the nucleus. So the more valence electrons you have, the more they can overcome those inner electrons that kind of shield it from the nucleus. So fluorine, neon are some of your smallest elements, whereas rubidium and francium are some of the larger elements. So it increases down a group, and if you're going from left to right, it decreases. So if you go right to left, it increases. The last periodic trend is ionization energy. And so ionization energy is the energy needed to remove an electron from an element in the gaseous state. So you have this element, you apply enough heat or energy to remove the electron. That's referred to as ionization energy. So what you can imagine is that metals have low ionization energies, non-metals have high ionization energies, at least for first ionization energies. So ionization energy decreases down a column because what happens is the atomic radius increases down a column, which pushes the valence electrons further out. So since the valence electrons are further out, it takes less energy to remove the electron. So as you go down a group, ionization energy decreases because the valence electrons are further from the nucleus. Now as you go from left to right, ionization energy increases because the atomic radius shrinks and those valence electrons are more tightly bound to the nucleus. So it increases as you go from left to right. So something like fluorine or neon would have very high ionization energy. Whereas rubidium or francium would have very low ionization energy. So metals have lower ionization energy than non-metals because metals, it's easier for them to remove electrons. So these are the periodic trends that you need to know: valence electrons, atomic size or radius, and ionization energy, namely what we refer to as the first ionization energy.